Welcome back. In this video lecture, we will show the Laplace integration property that will allow us to solve the so-called integro-differentiable equations that appear a lot, for example, in electrical circuits. So let's start first with the property. Now, let's say we have f of t, a function that is admissible. So that means a function that we can compute its Laplace transform. So that means that if I have f of t, I can compute its Laplace transform and I will call that f of s, okay? Now, this property tells us what goes on with the integral of this function ft, okay? So the Laplace transform of the integral is equal to the Laplace transform of the function but divided by s. Normally, I prefer this notation here, okay? Here we can see how the Laplace transform of this, the integral of the function is very easy to be computed. It's just the Laplace transform of f divided by s. Now, here it is very important to understand when we will see this type of functions. And I think a good idea is to think in an accelerometer. Nowadays, it's very easy to buy a sensor that measures acceleration. And from that, normally we want to compute, for example, the velocity. How can we do that? Well, we need to compute the integral between 0 and t of this acceleration function that is given by the sensor. So this type of integral between 0 and t of a function appears a lot in real applications, and this property of the Laplace transform tells us how the Laplace transform of this type of functions can be computed very easily, just dividing by s, okay? So I repeat here how the integral of a function, how we can compute the Laplace transform of that is just dividing by s. And it's noteworthy that when I compute the integral in time domain, in frequency domain, I'm just dividing by s. And if you remember, when I was taking the derivative in time domain, what I had in the frequency domain was a multiplication by s. And of course, this extra scalar term that we have to add. But I think it's a good idea to remember that what is taking a derivative in time is multiplying by s in frequency. And when I compute an integral in time, is dividing by s in the frequency domain. Okay? So let's now try to apply this property in order to solve what is called an integro-differentiable equation. Now, this here is called an integro-differentiable equation. That is because we have derivatives. So it's similar to an ordinary differential equation. We have derivatives there, but we also have a term that involves an integral. So that's why the equation is also called integral, because of this integral term. Now let's see how we can solve this integro-differentiable equation that is proposed here, okay? So we will proceed very similar to what we did with initial value problems. We will start by applying the Laplace transform to the whole equation, okay? When I apply the Laplace transform, what I get is that the Laplace transform of the whole left-hand side should be equal to the Laplace transform of the right-hand side, okay? Now, let's apply here the linearity of the Laplace transform. We know that the Laplace transform has the linearity property, so I can split this in the following way. Okay, now what I'm going to do here is to apply two properties. The first one is that the derivative in time in the frequency domain is multiplying by s. And the other property that I will apply is regarding the integral of a function. Remember that in the frequency domain is just dividing by s. That's that easy. So here we have the Laplace transform of the derivative. I apply this property here. In this term, we apply this property. And we get that this is s times capital Y of s minus y0 minus 2 times, and now in this term here, what shall we do? It's just definition. Remember that we decided to use this notation that tells me that when I have a function y in time, its Laplace transform is called capital Y of s. So this is just notation, and I will write here just capital Y of s. Okay, let's continue. Minus 3 times, and now what shall we do with this term? This is the Laplace transform of an integral term, so I will use the integral property that we saw at the beginning of the lecture, this video lecture. And we know that it's very, very easy. It is just to apply the Laplace transform of the function we have inside the integral and divide by s, okay? What in time is an integral, in frequency domain is dividing by s. That's it. Now, this should be equal to the Laplace transform of t, which is 1 over s squared. You can check that in your table of Laplace transforms. Now, here, we already solved the integro-differentiable equation in the sense that there are no derivatives and no integrals at all. Now, I will solve this algebraic equation. So what we have now is an algebraic equation where the unknown is capital Y of s. So what I'm going to do is try to isolate capital Y of s, okay? To do so, let me use the initial condition of the problem, y0 equals 1. So let's introduce this condition here. We know that y0 is equal to 1 because it's given by the initial conditions of the problem. So now let's try to take here common factor ys. It appears here ys, so there is an s multiplying. Also it appears here minus 2 times y of s, and again here with minus 3 divided s, okay? And then in the right hand side, I will have 1 over s squared. And also this term here, okay, this minus 1 will also go in the right hand side. So it will go with a plus, yeah, so that's plus 1. Now, in order to make it a little bit easier, let me multiply everything by s, okay? All the equation, okay? So that would be s squared minus 2 times s minus 3 equals 1 over s plus s, okay? I multiply all the equation by s to get rid of this divided by s here, okay? And now I can isolate ys. And let me do this here. Okay, this is, let's do this fraction summation here. Okay, so finally this ys is written as s squared plus 1, and then s times s squared minus 2s minus 3. So somehow, if you want, we can box this. Okay, this is the solution of our integral differential equation, but it's the solution in the frequency domain. Yeah? So somehow this is the solution, but we want to write down the solution in time domain. Okay, so now we need to go backwards to time. And in order to go back to time domain, we need to apply the inverse Laplace transform. Okay, in order to do so, let me write this down. Now we want to compute yt, which is the solution of our integral differential equation. But in order to compute this yt, we need to compute the inverse Laplace transform of capital Y of s, okay, which is this guy we have here boxed. Okay, so first thing is, when we want to compute an inverse Laplace transform of polynomial fraction, okay, we need to use, in general, partial fraction decomposition. So the first thing we need to do here is to check if we can compute here the partial fraction decomposition of this function. Okay, in order to do partial fraction decomposition, the first thing is that we need to know the roots that we have in the denominator. For example, here, I need to compute the roots here of this equation, s squared minus 2s minus 3 equals 0. Let me solve that. Okay, that's minus b. Okay, so here we have the result of this is 16. Okay, so the square root of 16 is 4. 4 plus 2 is 6, divided by 2 is 3. And the other root is when we use the minus sign. 2 minus 4 is minus 2, divided by 2 is minus 1. So these are the two roots that we have. So before applying partial fraction decomposition, we rewrite this where the denominator is factorized in its roots. Now we will apply partial fraction decomposition, which is, in this case, we have that each one of the roots is a simple root. You see here, all the powers are 1, so all of them are simple roots. So the way we will decompose this is a divided by the first root plus b divided the second root plus c divided the third monomial we have, s plus 1. Okay, so the one associated to the last root minus 1. Now, in order to compute a, b, and c, we can proceed in several ways. I will use something called Heaviside coverup method, because it's very fast for simple roots. I will give you a reference where you can check how this works out. I will just use it here. Heaviside coverup method, what I will use to find A is to multiply everything by S. Let me use another color. I think it will be better. It's like I multiply everything by S. Of course, when I multiply everything by S, I get rid of the s here, I get rid of the s here, okay? And now I will substitute the value s equals 0 in the equation. That will make this to be 0 and this to be 0, and only a to remain here. And here s will be 0, this s, and this s will be 0. And the result here in this left-hand side is 1 divided by minus 3. So minus 1 over 3. As you saw, this is very, very fast. Now I will compute b. Sorry, because one s was missing there. Okay. Now let's proceed to find b. In order to find b, you think that you multiply everything by s minus 3. I'm explaining Heaviside coverup method, in fact. Okay. If I multiply everything by s minus 3, of course these terms simplify and also these terms simplify. But also I'm going to substitute in here the value s equals 3. S equals 3. So 3 minus 3 here, 3 minus 3 is going to be 0. Here, 3 minus 3 is going to be 0. So here in the right-hand side, only b will remain, okay? Because 0 times c is 0, 0 times a is 0, so only b remains in the right-hand side. And in the left-hand side, okay, s is equal to 3, so s squared is 9. This s is 3, and here 3. So the result is 9 plus 1, that's 10, divided by 3 times 3 plus 1 is 4. So 3 times 4 is 12. So that's 5 over 6. And now we will do the last one, okay? I'm explaining Heaviside coverup method because it's very fast for simple roots. Okay, now let's go to the last term, c. In order to compute c, what Heaviside coverup method does is to multiply everything by s plus 1. When you do that, this term and this term simplify, this term and this term simplify, and then you will use the value s equals minus 1 here in the equation. Minus 1 times minus 1 is 1. Here you have minus 1 and minus 1. Now, what happens in the right-hand side is that minus 1 plus 1 here gives you 0 times a is 0. The same here, 0 times b is 0. And only c remains in the right-hand side. And what's the value of c? Well, this is 1 plus 1, that's 2. And the denominator, you have minus 1 minus 3, that's minus 4. But it's multiplying minus 1, so that's plus 4. So this is 1 over 2. So that's how you use Heaviside coverup method, which I think is very fast for this type of problems. Now, let's compute the inverse Laplace transform. YT, that's what we are looking for, is the inverse Laplace transform of this thing. Remember, a over s plus b over s minus 3 plus c divided s plus 1. But now we know the values of a, b, c. A is minus 1 over 3. Oh, let me use this step to also use the linearity property for the inverse Laplace transform. So we know that A, B, and C are constants, and by linearity, they could be written outside. So A is minus 1 over 3 times the inverse Laplace transform of 1 over S. Then plus B, which is 5 over 6, times the inverse Laplace transform of 1 over S minus 3, and then plus C, which is 1/2, times the inverse Laplace transform of 1 over S plus 1. Now, all the functions that appear here are given in the table, in the Laplace table. So we know the inverse Laplace transform of 1 over S, we know the inverse Laplace transform of 1 over S minus 3. All these inverse Laplace transforms are given in the table of Laplace transform. So this is straightforward. This is minus 1 over 3. Now the inverse Laplace transform of 1 over S is 1 plus 5 over 6. The inverse Laplace transform, remember that the inverse Laplace transform of the exponential is this. So here we are using this property to obtain the exponential of 3t plus 1 over 2, the inverse Laplace transform of S, 1 over S plus 1, that is the exponential of minus t. And that's the result, that's the final solution of our problem. This is the function in time that solves the problem we had initially, which is this one. Now, finally, as I said, this problem is it appears a lot in circuits. So I propose you to try to solve this integro-differentiable equation that is inspired in an RLC circuit. So try to solve it as an exercise. So that's it for today. Thank you very much. Bye-bye.